Okay, so we can start talking about diagonalizable matrices, which we started last time, but today we'll say the important thing about them. So diagonalizable. So just remember, yeah, the exam is on Sunday. Um, so I'm sure there's just about that before I start. Okay, so just as a reminder of what was happening, the idea was like if you have a diagonal matrix of the entries along, I'm doing everything first in the 2x2 case just because it's easier to understand. So if you have a diagonal matrix which is 2x2, the entries along the diagonal are just the eigenvalues. That's why I'm calling it a non-zero entry. That's why I'm calling those entries along the diagonal lambda1 and lambda2. And for a diagonal matrix, the eigenvectors you can find eigenvectors which are pointing in the directions of the x and y axis. So one eigenvector would be like E1, okay, and the other eigenvector would be E2. So E1 is like an eigenvector of lambda1, and E2 would be an eigenvector of lambda2. Okay, so here meaning being eigenvector just means that E times E1 is lambda1 E1, and E times E2 is lambda2 E2. By the way, there's nothing here that is nothing of what I've said so far requires lambda1 and lambda2 to be different. I mean, they could be the same, but I'm writing them in such a way which is like more general, where it looks like they're different, but I mean, it is fine if they are the same eigenvalue. But it's just better to think of them for purposes of like the pictures and everything, like as if they were different, but everything still works for the case where they are the same value. Okay. So the idea here is that you can think, well, that a diagonal matrix has like a preferred two favorite lines. One is the x-axis and the other is the y-axis, because those are the lines along which the eigenvectors are pointing. So I mean, it takes a little bit of thought, but some thought to see how you would generalize this. But the idea is to generalize this by saying that a matrix is diagonalizable if the same kind of still works, but now the eigenvectors are not necessarily E1, E2, they're just required to be like a basis of R2. So let me put it this way. So now if you have like a 2x2 matrix, you say that's diagonalizable. If there is if it has two linearly independent, if it has two linearly independent eigenvectors. So the idea for A is that maybe one eigenvector is here, so here's B1, and there's another eigenvector which would be V2. The fact that they're linearly independent just means that they're not parallel. So maybe V2 is pointing like, I mean, it doesn't matter when you how you draw it, like it could be like this, maybe V2 looks like this. Okay. So this is one eigenvector. So this would be eigenvector lambda1. And this would be like an eigenvector lambda2. So by that I just mean that A times V1 is lambda1 V1, and A times V2 is lambda2 V2. So I'm trying to draw them in a way that first, they could have different sizes, that's fine. And they also are not even necessarily perpendicular. The only thing that matters is that they're like two separate lines, or each eigenvector gives you a line and the lines are different. Okay. So the idea here is like to think that a matrix A is diagonalizable if it has like two favorite lines. And in a sense, that's kind of what for A will it is kind of like for A, like the real x-axis and the real y-axis in some sense. But I'll say that a bit more precise in a moment. So far, so good. Any questions up to this point? So we don't know what these vectors, eigenvectors are. So you can just call them like, I mean, V1, I don't know, it has two entries, X1, Y1, and V2 has two entries, X2, Y2, right? The cool, like the inside, is that, well, this is, you could think of this, once you have vectors, like one strategy is to assemble them into a matrix. That's kind of a lot of the philosophy of the course. So someone figure out, I don't know who it was actually. Someone figured out, well, let's just place them as a 2x2 matrix. First column is the first eigenvector, second column is the second eigenvector. So you create like a matrix of eigenvectors, if you will. So you have this Q matrix, which is like a matrix of eigenvectors. Which is like, just means like V1, V2, like the matrix whose columns are the eigenvectors. And so I mean by that, like the matrix whose entries are x1, y1, and x2, y2. Is that okay? Is that making sense? I mean, it's kind of like a clever thing to do. So if you do the product, right? I mean, it's kind of like an easy check, but if you do A times Q, right? I mean, this is like a, well, let me write it. You can do like, you can verify the algebra. If you, it's like a fun exercise to do. Oh, this is going to be a 2x2 matrix, right? Because it's a product of 2x2 matrices. And it is like a, like kind of a simple check that like the first column of this new matrix is just going to be what you get by doing A times D1. And the second column of this new matrix is going to be A times B2. I mean, it's like a, no, it's not like a bad calculation, it's just playing around a little bit with the multiplication formulas. So the first column is like the matrix times the first eigenvector. The second column is the matrix times the second eigenvector. Okay. But what is the matrix times the first eigenvector? Because it's an eigenvector, it's just lambda 1v1. And what is the matrix times the second eigenvector? Oh, it's just lambda 2v2. So is that making sense? So this is like, so if you want to write it more explicitly, this would be like lambda 1 x1, lambda 1 y1, lambda 2 x2, lambda 2 y2. Okay, that's kind of that's what I'm saying. You get, which makes sense because you're just multiplying the matrix by each eigenvector, right? Like so, you should just have obtained like the rescaled version of the eigenvectors. So that multiplication hopefully is reasonable. And then again, like it's kind of like a real, you just realize that this is the same as the matrix of eigenvectors times lambda 1, 0, 0, lambda 2. Okay. Right, because yes, it's you when you do this product, you get x1 lambda 1, and then you get x2 lambda 2, and then yeah, it's like a fun part. It's not too bad to verify. So what I'm saying, so this was the matrix that I'm calling Q, and this is a diagonal matrix, right? So what we're getting at is that AQ equals QD. Okay. And that's the fundamental equation for diagonalizable matrices. So let me write it down more explicitly. So if A is diagonalizable, Q is a matrix of eigenvectors. And D is the matrix of eigenvalues. Then let me put this in different colors because it will be useful. AQ equals QD. A times Q. But let me give you a second to copy this. But this is kind of like a matrix equation, so it's kind of better to write it in different ways. So for example, if I wanted to solve for A, right, how could you solve, what would you do in this equation to solve for A? If I just want to see this as A equals something.
I feel like the inverse of Q, like on the right side.
Yeah, right, like, so I want to multiply by the inverse of Q, but from the right, so that this cancels. So you just get Q, P, Q inverse. Remember, this matrix Q was invertible because it was made out of vectors that were linearly independent. That's where like it's convenient to write that down. Or like the other alternative way, which is useful to write it, is that, well, from this equation I could also solve for D, right? So how can I solve for D? Well, it's kind of like the same multiplied by the inverse of Q, but now I do it from the left to cancel this Q. So I get Q inverse AQ equals D. Okay, so all these three equations mean the same. They're all equivalent, but they're like different ways to think about the same equation. So let me write it down. So these three equations mean the same. Are the same. But maybe this is the one that's more clear why it's called diagonalizable, because it means that if you take the matrix A and kind of multiply it by a clever matrix, it becomes and its inverse, it becomes diagonal. So in that sense, I mean, that's another sense in which maybe the name is justified. Let me give any questions about this. Okay, let's try to do this in one example so that you see what I mean. Then I'll tell you some fun things you can do with these matrices. So let me try to see if I have a nice one here.
Always be vertical.
Yes, because I mean, by assumption, what makes a matrix diagonalizable is the assumption that the eigenvectors are linearly independent. And that's what guarantees that the determinant is not zero. Yes. Okay, yeah, let me do a cool one. I like this. So, and I'll just ask for someone to remember what the answer is because we'll use it later. So let's say I give you, here's some example. Let's just check it from like, just so that you see in practice how things would look like. Let's say I give you this matrix A, right? Which is kind of easy. Just a simple 2 by 2 matrix. And this matrix is not diagonal, right? It's not a diagonal matrix just because here you have something that's not zero, right? Okay, so let's check whether this would be diagonalizable or not. So first you have to find the eigenvalues, right? So what are the eigenvalues in this case?
One and two because it's upper triangle.
Right, it's upper triangular, so the eigenvalues are just 1 and 2. And I chose a number so that it actually even matches like with the index. So like it's a nice matrix. So for like, what is that? Like the eigenvectors for lambda 1 equals 1. Well, you look at A minus lambda I. So it's A minus, because this is 1, it's A minus the identity, right? So you get 0, 3, 0, 1. Right. So again, you have to look at the null space of this, which gives you 0, 0, 0, 0, 1, 0. Okay. Okay, so let's see. This is going to be 2e. Oh, it doesn't matter if it gives you the. Okay, so this forces right. What happens here? This is forcing y to be 0. Is that making sense? So if you remember, like the eigenvectors were like x comma y, but it becomes x comma 0. So it's x 1, 0. So one eigenvector, right? One eigenvector, I was using, I don't remember which color I was using here. So the eigenvector would be b1 equals 1, 0. Right? That's the eigenvector for lambda equals 1. So first, up to this point. So let's do lambda 2 equals 2. So now you look at a minus lambda I, right? Is now a minus 2, the identity, right? Because the eigenvalue is 2. So when you do that, you get negative 1, 3, 0, 0. Okay. So I mean, the null space in this case is kind of easier. I mean, like there's no reduction needed. This is telling you that minus x plus 3y equals 0, right? So you know that x equals 3y. Right. So if you take a vector xy, this is what? Sorry, x is now 3y, so it's 3y comma y. This is y, 3 comma 1. So the eigenvector, I'm writing them as columns. Again, it is important for building up the matrix. So the eigenvector is the eigenvector v2 is 3, 1. So far, do you agree with it up to this point? Any questions? So what's the matrix of eigenvectors? The matrix of eigenvectors is just the matrix whose columns are these eigenvectors, right? Is that okay? And we also need the formula. I mean, we also need the inverse of the two, like of these 2 by 2 matrix. That shouldn't be too bad, but because we just have to reduce it to the identity, right? If you remember, what we need to do. I think the inverse was going to be like, let's see if we did like. Is this the inverse? That's my god, I probably am not doing anything. These two multiply to the identity, right? Is that correct? Let me know if it didn't work. Suppose I work with everyone. Okay, so my claim is that if we did Q inverse AQ, we will get like a diagonal matrix equal to the eigenvalue. So let's just check it out for fun so that you see it does work. So if we do Q inverse AQ, Q inverse AQ, it would be 0, -3, 0, 1, A was 1, 3, 0, 2, and Q was 1, 3, 0, 1. So I mean, we can multiply these two first. So when you do this with this, you get 1. When you do this with this, you get 3 minus minus 6, so you get -3. And then this one gives you 0, and then this one gives you 2. Okay, and hopefully this will give you something that's diagonal. So this one with this one gives you 1. This one with this one gives you 0 again. This one with this one gives you 0, and this one with this one gives you 2. So it's a diagonal matrix equal to the eigenvalues. Okay. That making sense? So it was kind of, you make a diagonal in like you had like a matrix A, which was not diagonal, but this process makes a diagonal in some sense. Like the more, like what's really going on is that again, you have the x and like the problem in this course is that we kind of think of x and y as being fixed axis. But what you should really think about is that you make a change of coordinates, like if you want to think about it more physically. So once you make a change of coordinates, you can kind of rewrite the matrix in the new coordinates, and in the new coordinate system, the matrix looks diagonal. So that's really what's going on. But it's a little bit more like of an advanced point of view on what's happening. But it's kind of like you take x and y and rotate them or whatever you need to do so that they align with the new, to the line with the lines of the eigenvectors. And with respect to those lines, like the matrix the plan. Is that okay? Okay, so let me give you some applications. By the way, as you may imagine, like in the 3 by 3, 4 by 4 case, it's essentially the same. You just need like, instead of 2 linearly independent eigenvectors, you need 3 linearly independent eigenvectors or 4 linearly independent eigenvectors. Everything else works exactly the same way. There's not nothing new. So before like just writing that down, let me give you some applications of doing this. Okay. Okay, so one application, so here are some applications of diagonal. So some applications of diagonalizing. So the first one is that it gives you a very easy way to find the powers of a matrix. So it gives you a quick way to take powers of a matrix. So what do I mean by that? I'll also have to give you an example of a matrix which is not diagonalizable, but there are plenty. So that's not. I'll do that later. Just remind me to give you an example. So what do I mean by this? So remember, A is diagonalizable. So here A is diagonalizable, which means that if you look at that equation, this is like kind of like our master equation that A equals Q D Q inverse, or I mean any of the three versions, but this one is very useful for what I'm about to say. Okay. So let's say I wanted to find A squared, right? So what would be A squared? Well, in general, that's just A times A, right? I mean, and if you knew nothing about the matrix, you just have to start doing like the random products, right? Like of the entries, like using the matrix multiplication. But if you know that this is diagonalizable, what does this become? What is A? Well, it's Q P Q inverse, right? And what is A? Is Q P Q inverse, right? So what do we get? Q D Q inverse, Q D Q inverse. Is that making sense? Which doesn't seem that useful, but it's actually a lot easier. Why? Because there's something I can use here to simplify it a little bit more.
Q inverse times the Q is just the identity.
Right, this Q inverse goes away because it's the identity. Okay, so this gives you Q, and then there's D times D, that's just D squared, right? Q inverse. But the thing is, like, this is the square of a diagonal matrix. What's the square of a diagonal matrix? Like, it's just the square of the individual entries because it's diagonal. So I should write that down. Like, if D is lambda 1, 0, 0, lambda 2, D squared would be, for example, like lambda 1 squared, 0, 0, lambda 2 squared. Okay. So the idea is that A squared, right? A squared would just be Q D squared Q inverse. Okay. So, and what would, like, if you had to make a guess, right? What is A cubed? Based on this logic, what would it be?
Q E Q Q.
Yeah, that's a cool thing. So Q D cubed Q inverse. So what I'm trying to say is that if you want to do A to the N, right? That's just Q D to the N Q inverse. Okay. And that's a lot easier. Like if N were like 20 or 30 or whatever number, that's a lot this is a lot easier to do because like the powers of the diagonal are just straightforward. You just take the individual powers of the entries. Versus like having done like the product, you know, as like ordinary 2x2 matrices. So for example, just to give you an idea of how this would look like for our matrix A, right? The matrix A that we had before was 1, 0, 2, 3, right? What I would be saying is that a to the 4, right? And here, like the diagonal matrix was, it's just a matrix of eigenvalues, it's 1, 0, 0, 2. So a to the 4 would be q e to the 4 q inverse. But what is q? Q is 1, 3, 0, 1. What is d to the 4? D to the 4 is 1 to the 4, which is 1, right? 0, 0, 2 to the 4, that's 16, right? And what is q inverse? It's still 1, negative 3, 0, 1. So that's the fourth power of this matrix. And then this is not such a bad multiplication to do, right? But just compare that. If you knew nothing about diagonalization, compare doing this 4 times, like, a times a times a times a times a. It would be very tedious. But here it's just like multiplying 3 relatively easy matrices. Is that making sense? So here it saves, you can see that it saves you a lot of time to be able to do this. Is that okay? Okay, I don't want to erase this because let me just keep this here if needed. So I will just refer to this for the next example as well. Let me give you a pen of this. Okay, so another example which I really like is that it gives you a way to find the exponential of a matrix. So let's start to talk about this one. So this is application 2. Gives you an easy way to compute the exponential of a matrix. Gives you an easy way to find the exponential of a matrix. Okay. So this just to motivate this idea, I may need a couple of just a few quick minutes on reminder of Calc 2. Maybe I think this is where it happens. So if you haven't seen Calc 2, don't worry about it. You won't need this anywhere else. But it's kind of like a nice motivation for what I'm about to do. So what's e to the x like? So in Calc 2, I think you learn about Taylor series, right? So there is a way to write this as a series. Anyone remembers the formula for this series? Yeah, good. So it's kind of like e to the x is like 1 plus x squared over 2 plus x cubed over 6, but 6 is 3 factorial, blah, 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 blah. And this is, if you, at some point, you would learn that this is like, if you haven't seen it, then don't worry about it. It's x to the n divided by n factorial. That's kind of like a useful way to work with an exponential function. Then the idea would be, well, if you wanted to define the exponential of a matrix, you just go with this formula and see what happens. Like, that's not a silly thing to do. What would be the analog of 1 in the world of matrices? Identity, right? So you should put like identity plus x, but x is like what I'm calling the matrix A, plus x squared becomes a squared over 2, plus a cubed over 6, blah, 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 blah. And so really like the exponential of a matrix should be a series which is a to the n over n factorial. Okay, that's actually the definition that works best for defining the exponential of a matrix. But, right, so let's just work with this. I'm saying that the exponential of a matrix would be this series. But if the matrix happens to be diagonalizable, right? If the matrix happens to be diagonalizable, we have a formula for the powers of a matrix A, right? So it just becomes Q e to the n Q inverse over n factorial. Okay, and the thing is like these Q and Q inverse do not depend on n, so you can pull it out of the series. So really you can write it as Q times this So like the formula for the exponential of a matrix should just be Q times e to the d, where d is a diagonal matrix times Q inverse. Okay, and then you just have to figure out what the exponential of a diagonal matrix, but just like that's just the exponential of every term along the diagonal, basically. So let me write that down. So if A is diagonalizable, one way to define the exponential, you can define e to the A as Q e to the D Q inverse. Or here again, D was the matrix of eigenvalues, and e to the D is e to the lambda 1, 0, 0, e to the lambda 2.
Why is bottom right hand tree like 0? Wait, no.
Oh, we're talking about here?
And D.
Oh, sorry. It should be lambda 2. Thank you. Perfect. Now we're good. So let's try to see how this looks like. It's nice to see like some exponential matrices in practice, so that you have like a better idea that it does look like some exponential. I mean, it is not like a bad name. It does have like some exponential flavor to it. So let's try to see how it looks for this matrix actually. It doesn't, I mean, again, like the exponential can be defined without being diagonalizable, but it's then the power series. And dealing with that is kind of like a mess in general. So if you want like a useful formula, like in the diagonalizable case, it's fine, easy to find like a useful formula because you just have this one. So if I gave you this matrix, and I can promise you in the final there will be a question where I ask you to find the exponential of a 2x2 matrix, because it's like a classic problem of matrices, like, and it's useful to have it around. So if this is A, this is D. What is e to the D? E to the D just means exponentiate the entries along the diagonal. So it's e to the 1, 0, 0, e squared. So just e 0, 0, e squared. Okay. And we're almost done. What's e to the a? E to the a would be q e to the d q inverse, but q is 1, 3, 0, 1. E to the d is e 0, 0, e squared. Q inverse is 1, -3, 0, 1. Okay. And again, you just do this product. So for example, if you multiply the first two matrices, you get E, you get 3E squared. Yes. Then you get 0, right? And then you have E squared. And this is times 1, -3, 0, 1. And when you do this product, you get E, you get -3. Okay, let's see. -3. Okay, let's see. I think I got the formula here, so let me check if it is the correct answer. Oh, okay, yeah, it's fine because like it's not the one. Is that making sense? So it has like exponentials in its entry, so it kind of makes sense that this would be called like an exponential matrix. You see?
This also works with like sine, cosine, epsilon.
Right, it is, yeah, so if, it's just that the exponential is kind of, deserves its own line, but like, yeah, I can give you the general formula. So the idea is like, if you take your favorite function of, calc 1, right, f of x, where should I write this? So yeah, like the generalization of this is the following. So here's like the generalization. You have like the function of one variable. Your favorite of one function. So it could be f of x equals e to the x, or f of x equals square root of x, or f of x equals ln of x, f of x equals sine of x, cosine of x, whatever you want to think you could write in the world, like you put it like as your favorite function there. Then if you have like a diagonal matrix, right? For a diagonal matrix, what is the function of this diagonal? F of d is just what you get by applying f to each entry along the diagonal. So it's f of lambda 1, 0, 0, f of lambda 2. So what I'm saying here is like if this were like the cosine of d, it would be cosine of this entry, cosine of that entry. Or square root of d would be square root of that entry, square root of that entry. Obviously, that requires certain conditions. For example, for taking the square root, you need the entries to be non-negative. So assuming that you could evaluate it, then this is well defined. And then f of the matrix A, f of A would just be q f of d q inverse. Okay. Which is like the analog of this, but for the exponential, right? Like that's the special case where this was like the exponential. So what the logarithm of A, it would be q logarithm of the diagonal matrix times q inverse, the same for square root, the same for everything else. So if you were curious, because like the eigenvalues here were positive, so you could take the square roots of these of this, sorry, you could take the square roots of this eigenvalue. So the square root of D, in this example, for example, D was 1002. So the square root of D would be 100 square root of 2, and the square root of the matrix A. I mean, this is not you. This is typically not how you would write it. It's you would write it more deep to the 1/2 actually. So let me write it like this. More common notation for the square root in this context. So you would write 1302 1/2 is Q1301 times the square root of this 100 root of 2 times the other one, 1-3. That makes sense? And then, well, you just do the product, and whatever that is like the square root of that matrix. That makes sense? It's kind of clever. I mean, it is kind of like a nice application to have around. And this actually, I mean, if you take differential equations, this exponential thing, it can be used to solve like linear differential equations. Basically, you just you have like a linear system. You have seen that you can associate like a matrix to that system, and then the exponential of that matrix is more or less a solution. I mean, you have to multiply by a t or whatever, but I mean, like it gives you like an elegant way of differential equations if you have to do that at some point. I think it's sense. So yeah, it's like a nice, but I will just ask you the exponential matrices because that's kind of my favorite one. But just so you know, you can take, it's not that it's exclusive to the exponential. You can take again logs, cosines, sines, square roots, cubic roots, things like that, very easily in the diagonalizable. Okay, yeah, so those are interesting applications of diagonalizability. Let me just give you I haven't given you an example of a matrix which is not diagonalizable. Then I'll tell you how this looks like for 3x3, 4x4, but it's essentially the same, just with more like eigenvectors needed. So, and then this way we can wrap up this eigenvalues topic, and then after the exam next week, so next Wednesday, we'll talk about perpendicular subspaces or orthogonal subspaces, which is also a very interesting part, like linear algebra. Yeah, so the PDF has another example, but so yeah, here's an example of a matrix which is not diagonalizable. This is very innocent looking matrix, right? It's like it only has one eigenvalue actually, which is just 0. 0 is the only eigenvalue. Only 0 as eigenvalue. Right, and so if you do A minus lambda I to find the eigenvector, right? Like this A minus like the 0 matrix, right? So just A. So you get 0, 1, 0, 0, and you would augment this to the zero vector. And there's not too much that happens here. It just gives you y equals 0. Right? So again, if you take xy to be a eigenvector, it's just x comma 0. Right? Sorry, it's x times 1, 0. So any eigenvector is a multiple of E1, right? So any eigenvector of this matrix is a multiple of E1. Does that make sense? So if you wanted, like, the thing is that this cannot be diagonalizable because for diagonalizing the matrix, you need at least two linearly independent eigenvectors. But any other eigenvector you find is a multiple of this one, so this will never be linearly independent. Another way to say it is that you choose this one as the first column, then the second column would be a multiple of this one, so the determinant is 0, like it's like the matrix won't be invertible. So there's just no way to diagonalize this matrix, like it cannot. So A can't be diagonal. That making sense? So sometimes even the easiest matrices, they just fail to be diagonalized. So so I felt like yeah, I should at least give you an example that you see that one that's not diagonalizable. So now let me give you the general case, like n by n. So in the n by n case, you just need n linearly independent eigenvectors, basically. So so diagonalizable matrices. General case. So A is n by n, and it is diagonalizable. If it has n linearly independent eigenvectors. E1 up to Bn. Okay. And everything that I just said continues to work here. So what you can do is call the matrix of eigenvectors Q. It's just that now it's more like more general. This is like a matrix with columns are the n eigenvectors, right? the matrix whose columns are the eigenvectors. Okay. Because they are linearly independent, the determinant of this matrix is non-zero, so the matrix is invertible. And then what you can check, I mean, it's nothing of what I said, it changes at all. So you have like the same basic equations. Let me write them again. So you just get the same as before. You get that A times Q equals what? Q times D, right? Where D is like the matrix of eigenvalues. Or you also get that Q inverse AQ is the same as D, or that A is the same as Q D Q inverse. So again, like the same three equations from before, it continues to work. Is that now you're just working with n by n matrices, okay? And all this, like again, I won't ask exponentials for like a 3 by 3 or thing. I mean, it can be done. It's just like a little bit more tedious. So like if you wanted to find the exponential of this matrix, it would be Q times the exponential of this diagonal times Q inverse. Nothing changes. The same story. There's nothing new here. So if you want, I can just give you an example of 3 by 3 how it looks like, just so that you have like an idea. It's on the PDF. No, it's fine. Yeah, the most I would ask you to diagonalize in practice for us is like a 3 by 3. More than that is like I mean, it's just so much work. So I would even for this problem, probably I will give you either the eigenvalues or something so you don't have to start from 0, because otherwise it would just take an eternity. So 2 by 2 is fine. Like you can kind of do 2 by 2 very easily if you put like the strategic numbers. But yeah, more than that is kind of long. So like for example, if I gave you this matrix, right, you can just check that you can check that lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals -1 are eigenvalues. So and you can also check. I mean, it's all done in the PDF, but redoing this is so I'm just praying here that there are no typos. Yeah, we could put this. All right, vectors. Are the corresponding eigenvectors. Okay, so here you would build like the matrix Q, which would be this like the same ones as -1, 1, 0, 1, 1, 1, -1 half, -1 half 1. And like what I'm trying to say is that if you want to do the work on your own, like you can find the inverse of that one. I actually didn't write the inverse on the notes, but I mean you can find the inverse of this matrix, and then you would check that you can check, for example, that when you do Q inverse times A times Q, right? You would find the diagonal matrix, and the diagonal matrix would just be this eigenvalues, 1, 2. But you see, like even this one is multiplying 3 by 3 matrices, so it's kind of tedious, finding the inverse of the 3 by 3 matrix. There are a couple of like many steps involved. So yeah, if I give you a 3 by 3 matrix, it would be one where like the inverse is kind of easy to find, so that you don't want to spend too much time finding the inverse or things like that. The only thing that I should say, which is not maybe clear from, may not be, I may have been implicit of what I have said, but just to make it explicit. So if the first column, if the first column uses this eigenvector, the first column here should be the eigenvalue corresponding to that eigenvector. So you cannot put like eigenvalue 2 here, right? Because eigenvalue 2 is related to this other second column. So I'm just saying, like, do not mix the columns and the eigenvalues, right? So an eigenvalue comes with an eigenvector, so they have to appear in the same order, right? So first eigenvector with its corresponding eigenvalue here, second eigenvector with its corresponding eigenvalue, third eigenvector with its corresponding eigenvalue. So it's not, you're not allowed to just like mix them up. Otherwise the multiplication won't come out correctly. Yeah.
Like, for example, if your eigenvector is like some scalar multiple would still work.
Right, like, yeah, so like, for example, yeah, maybe you don't like the 1/2, so you multiply everything by 2, right? So if you multiply everything by 2, this like becomes -1, 2, but that also affects the inverse, right? So like that thing is like the kind of the effect cancels out because of the inverse here. But yeah, when you do that, so I'm just saying like Q is not unique, right? Because you could rescale the eigenvectors, for example, or you could also like say, why did I come up with the idea that this should be the first one, the second, the third? Maybe you want to do this one as the first one, right? So that also changes the order of the columns. So this breakdown of the matrix is not, and there are different ways. I mean, there are several Qs you could find, etc. But they all have the property. If you do it correctly, they all have the property that when you do Q inverse A Q, it will give you the matrix of eigenvalues in the order that you chose them. Does that make sense? Any other questions? But yeah, so for now, this diagonalizable thing, I'm more interested, more like, yeah, I give you like a 2 by 2 matrix or something like that. I ask you to find an exponential. I like those problems. I think that's a nice application of diagonalizing matrices. And then later, towards the end of the course, we'll like, there's another big theorem in linear algebra that says that a matrix which is symmetric, if you remember, a symmetric matrix is one where A equals A transpose. All symmetric matrices are diagonalizable. That's one of the biggest theorems in linear algebra. So once we get there, it's just that in that case, you can say a little bit more stuff about how the diagonalization looks like. So for that, it's useful to discuss a little bit more first about perpendicular vectors and orthogonal subspaces, which is what we would do after the exam. But yeah, it is a nice thing to say. And like, so for example, I think I can mention, I may have asked you to watch these YouTube videos before, like you have like if you have like a solid object, you have like an inertia matrix, and that's a symmetric matrix. And so it can be diagonalized, and the eigenvectors for that matrix are called the principal axis of inertia. So those are like the axis, like the directions in space, where like a rotation, where the angular momentum is parallel to the angular velocity, basically. I mean, I'll tell you more about that once we get to that point. But it does have many applications, that the fact that some symmetric matrices can be diagonalized all the time. So, but yeah, I think that this is actually where I wanted to end for today, because I don't want to start the new topic because since we have the exam on Monday. So if there are other questions, yeah, I'll just see you on Monday. But yeah, for the exam, just practice the PDF problems, the review, watch the review videos, like the 2 review videos, and like is kind of very similar to the examples I done in class and the PDF and those problems. So like there shouldn't be any surprises if you did that. So. And again, the two problems will be from those from that list. So that should give you an incentive to resolve that. But yeah, no, I'm bugging.